Hi everyone. So this video is actually an interesting way to sort of combine the two things we have been doing in class. So the first thing that we did in chapter 9 was we discussed the concept of boundary layers. Uh, so basically that is a flat plate as shown here. So in the red color you can see this flat plate and the fluid is coming on a velocity u, and near the wall, basically because of no slip condition, there is some layer where which is basically known as boundary layer, like shown here, like boundary layer, where you see some decrease in velocity, right? So this is something that we have discussed in class, but these days, this week in the class, we are discussing macroscopic balances. So what this video tries to do is sort of combine the two things we have learned. One is the boundary layer and one is the macroscopic balance, and the purpose is to sort of do a macroscopic balance on a boundary layer given here, such that we want to find this average wall stress applied on this plate because of the fluid flow. So you should remember that in macroscopic balance, one of the things we want to do is that without solving for the flow profile, we want to estimate the effect of flow on the walls of the physical system we are looking at. So for instance, if it was a pipe, we were trying to understand the forces caused on the due to bending, or just forces caused due to just flow of the fluid in the pipe, right? So similarly, we are trying to find here the stress is basically force per unit area on the whole plate because of the flow, and that happens because of the boundary layer itself. So this is something we have discussed, that this happens because the boundary layer develops where there is a velocity gradient. So the velocity changes as a function of the y coordinate. So let's call this x, this is y. So there is a velocity which changes as a function of y and then basically becomes constant outside the boundary layer, becomes equal to the free stream velocity, right? So this is something we know, we have discussed, but what the purpose of this video is trying to see, to use macroscopic balance to estimate wall stress by the fluid on the uh, on the uh, on the plate. So there are two parts of this problem. One part is this A part, and you can imagine that whenever we are trying to do a macroscopic balance, we need a control volume, right? The first thing we need is a control volume, and the control volume allows us to define the scope of basically the balance we're trying to find, this force which we are trying to find. The second thing we need is the information of pressure, right? Something we generally care about is the information of pressure, and for a macro we also need information of velocity square averaged, right? So these are the some things we really care about. And what this problem is telling you is that analyze the tau naught for two parts. A part where you can assume the velocity profile to be linear. So we know the velocity is 0 here, and at the edge of the boundary layer, which is at a distance delta, and delta is a function of x is this coordinate, and it increases over x, that it will vary by uy by delta. So for each point as a function of x, it is a linear, just like a shear flow, just a linear velocity profile. This has been given to us, something you don't have to worry, but this has been given to us. The second option is that it is given to us, it's a parabolic profile. Again, this is something in pipe flow. This is similar to shear flow, this is something similar to pipe flow, and the expression of the velocity is given to us. So what do we mean by these velocity profiles? This is something we have not discussed in class. So if we assume linear profile, if you put y is equal to 0 at y is equal to 0 here, you get velocity to be 0, right? And if you put y equal to delta, you get velocity to be capital U, which is the velocity of the free stream flow. So basically just trying to show you that at the ends, you have the same velocity which you really care about. In the case of parabolic velocity profile, if you put y is equal to 0, again you get u is equal to 0. So at the edge here, velocity is 0, but at y equal to delta here, If you put y equal to delta, you get 2 minus 1, which means the velocity is again u, or the free stream velocity. So both of these velocity profiles basically do correspond to the correctly to the ends of the velocity spectrum, that we expect that at y is equal to 0 velocity is 0 and y is equal to 0 velocity is capital U. However, I should add that these are not the exact descriptions. This is just an approximation, and what you can imagine is that what will change is the velocity square average for the two profiles will be different, right? So this is something we know that we need to do any macroscopic balance. Now, how should we even approach this problem? How should we start this problem? So the first thing we realize is that we need to calculate tau naught, or the wall shear stress applied by the fluid while it is flowing over this plate. So because we want to calculate on the entire region, you can imagine that I would prefer to have a control volume like this, which is of boundary layer delta as a function of L here, and this is because in this region here, in this part with y equal to L, this is the region of the maximum boundary layer, and here is velocity will follow this profile, and at the leading edge here, this part velocity will be basically like constant. It will be u everywhere. So this is a natural control volume which comes out, which is a rectangle. So let me mark this in the control volume in red. This is our control volume. This part is control volume. Okay. So again the reason is that above this height, above y is equal to delta, above here everywhere the velocity is free stream velocity, so there is no difference in the velocity. If there is no difference in the velocity, then you will basically not get any contribution because of that. And you imagine that if we did not account for the boundary layer, we'll get no drag, right? This is something we have discussed. So we just care about the region of the where the velocity is changing here, and we just draw a rectangle here because here the velocity is, this part is the velocity is constant, and here the velocity we know is a function of the y coordinate, right? So this is the choice of our control volume. So again I emphasize that our, just to be a little more clear, our control volume is like a rectangle here. This is the delta of L here, and the reason is that the velocity is constant here and it is changing here. Okay, right. So this is something we know now, and of course here this fluid will apply some force on this bottom part, and we need to basically calculate the force and divide by the area to calculate this wall stress. Okay, now the second thing we need to do is to estimate pressures. And the third thing we need is the information of V square. So for estimation of pressure, you can recall that the pressure is actually constant everywhere in a flat plate, and this happens because you may recall that the dp by dx in the case of in the case of a flat plate, this is something we have derived, is minus du by dx, or the external flow. If there is some change in external flow free stream velocity, we have some change in pressure, but we know the free stream velocity here is stays constant over a flat plate. So if this is a curved plate, yes, there will be some change in the pressure, but because this is a flat plate, there is no change in the pressure, or du by dx is 0, so dp by dx is 0, or which means pressure is constant. So this is very straightforward. This tells us that pressure is constant. We have a control volume that we care about, and then information of v square is pretty straightforward for us because we have been given velocity profiles. So with that, we have a control volume, we have information of pressures, and we have information of velocity square. Like we can calculate this velocity square mean. Let's do the balance. So let us first see how many surfaces we have. So in a macroscopic balance on a control volume, you identify the surfaces. So we have 1 to 3 surfaces which are open, and this 4 surfaces are wall. So basically our F star, or the force which we carry in the macroscopic balance would be only on the uh, would be because of the wall part, right? That is the wall part. Now the third surface here has no normal component of the velocity. So the velocity here at the surface, which is the surface like this, everywhere the velocity is only in x direction, and so outside the boundary layer the velocity is just in x direction, and this the whole top layer is outside the boundary layer, and this at the end here this is the corner of the boundary layer, but it's still at the top of the boundary layer. So everywhere at the top the velocity is just parallel, so velocity is just like this here and equal to the free stream velocity. So there is no normal component of the velocity, and you can remember. So this is something that we have not discussed in class specifically, but there is a component like v dot n which comes in in the in the in the case of macroscopic balance. Naturally, this is zero in this case, or you can even physically imagine that there will be no momentum inflow because the velocity is parallel. So momentum inflow is only through here. So because there cannot be any mass inflow, so there cannot be any momentum inflow from the top surface. So third surface is basically like a wall for us, similar to a wall, not exactly a wall, in the sense that there cannot be any mass flow. So the two surfaces we care about is 1 and 2. And if we remember this, so and if we write n1 vector, so n1 vector will point to minus ex, n2 vector will point to plus ex. If we do that, we can actually write our balance very easily. If you recall, this is how we did this. Minus of ex, because n1 is minus of ex. This is plus ex. In other words, this becomes simply, this is minus of ex. Let me just erase this and correct this in case there is any confusion. Ex into p1 minus p2 plus rho v1 square average minus v2 square average, right? And in simple form, this just becomes rho into v1, because p1 is equal to p2. Again, because of this, that the velocity no longer changes in the free stream, it only changes within the boundary layer. Free stream velocity doesn't change, dp by dx is 0 or p is constant. You can just write v1 square minus v2 square. Okay. So now we have our force, and it is in the x direction. So this is very simple now. If we once we know this, you can write force. Sorry, my mistake. I forgot to multiply the whole thing by the area. So sorry, just correct. Let's correct this. Sorry. So this whole thing is, remember, it is pressure times rho v square into normal times the surface area. So that's my mistake. I'm sorry. The surface area of this surface is delta times this width of the bond of the plate. So it's everywhere multiplied by delta w. So please correct it. I'm sorry for that. It's delta times w. Right. So this is, just correct this part. I forgot to multiply. So in the macroscopic balance, it is pressure plus rho u square, which is the part multiplied times the normal into the surface area. So this was, I forgot to, because this is the force. You have to multiply by surface into delta into w. So basically, this force actually becomes rho into v1 square average minus v2 square average times delta w. Okay, and I hope this makes sense that I've just multiplied by the surface area, and surface area is the cross sectional area. Sorry, in this case, is delta times the width of the plate. So I hope everyone can imagine this area. This is width and this is the delta. So similarly, the force is acting on this shear stress is acting on the bottom part, and shear stress will be stress times, shear stress can be then written as delta into length into width, because the length it's acting on the entire plate and then in the width direction is equal to, basically I'm just taking the magnitude now, rho v1 square average minus v2 square average u, and then w gets cancelled, and then the tau actually becomes rho into v1 square average minus v2 square average and delta by L, right? This is what we get. So this is the stress that we are after, or you can call it tau naught. It's the stress we are after, and it basically depends on this v1 square and v2 square. You can imagine if I assume the velocity profile within this boundary layer to be flat, or that the velocity profile is constant everywhere, that it is just capital U everywhere, this will go to zero, because we know that the capital v1 square will be actually u square, because the velocity profile is just same everywhere in the initial region here, or the initial region here, everywhere is it's u, so it will basically be u square. So we have to evaluate the velocity profile in the second region, but we know the velocity profile in the first region, the square of the mean, the mean of the square velocity in the first, we know it's flat, so everything will be capital U square. The second region we have to evaluate, but if it was everywhere was uniform velocity, this will go to zero, which actually goes back to the paradox that we were discussing, that there will be no drag or no stress on the flat plate if you do not consider the variations in the velocity in the boundary layer. So I hope it makes sense. What we are saying is that v2 square cannot be capital U square, because we want to have some drag, because if v1 square is basically capital U square. So let's write v1 square is capital U square, and why is that? Just to recap again, the velocity profile is uniform here, so if you just want to do the average, it will just be the square of this. But here we have two cases. The first case is for the v2 square. The first case is that we have to assume the velocity to be linear, and the second case we have to use the quadratic. So first let's assume linear, which is uy by delta, uy by delta. So if we want to find the square of this, we'll take into dy from 0 to delta by dy 0 to delta. There, we can also multiply by the width to find this, but I'm just not doing it out of simplicity, because you want to, whenever you take a mean, you multiply by the cross-sectional area through which it is flowing. In this case is dy into the width, but width is cancelled out from the numerator and denominator, so I'm not taking that. This becomes actually y square by delta q, so one delta comes from here, and then dy from 0 to delta, and you can imagine that this becomes u square into 1 by 3 y cube by 3 delta cube 0 to delta, and this becomes u square by 3. Okay, so this is pretty straightforward. So now we have a tau naught, and we know that this is not equal to 0, because v2 square is u square by 3. It is not u square, so this will not get cancelled, and we'll have some finite stress. And then we can also do the same for the other case, in which we have a parabolic velocity profile, which is u into 2y by delta minus y square by delta square, now whole square of this times dy from 0 to delta dy. Okay. Again, recall the fact that we had initially the velocity in parabolic form, 2y by delta into y square by delta square, and that is what I am doing here. Now we can easily do the integration of this also. We just expand the square, so that will become u square. So this was u square, because it was the whole of square, so this is u square. U square into 4y square by delta square which is the square of this, plus y4 delta 4 minus 4y cube by delta cube. Right? This is how we will open up this square which is in the brackets. In the bottom we have delta. So if we do the integration, within the brackets, it is not very difficult to see that this will become 4 y cube by 3 delta square plus y5 by, sorry, my mistake, there's a typo, small typo, so delta 4 because I have square y square by delta square, so y5 by 5 delta 4 minus 4 by 4 by 4 delta cube 0 to delta. Okay, this may look a little bit of bad, but I'm sure you can do it very quickly. It's just basic algebra, just squaring this. Y square integration is y cube by 3, y4 integration is y5 by 5, y cube integration is y4 by 4. Okay. So if you do that, you can very easily see this will become y square. Every delta would basically get cancelled here, and if y validated at 0 is 0, so this basically becomes 4 by 3 plus 1 by 5 minus 1. Okay. And if we evaluate this has, we will take a denominator 15 here, it will become 8 by 15. Check that. This will 20 plus 3 minus 15, so basically becomes 23 minus 15, so 8 by 15. And in other words, v2 square in the case of b part, the parabolic velocity profile is v square 8 by 15. Okay, so we have both v square now, so we can evaluate tau naught. So let's do that. So recall again, our tau naught average was rho into v2 square, v1 square minus v2 square average into delta by L. And in this case, this actually becomes, for part A, the tau naught average, you can rho into u square minus u square by 3 into delta by L. And this becomes 2 by 3 rho u square delta by L. And if you remember from chapter 3, something we discussed was the skin friction coefficient. You can calculate that by dividing this by rho u square by 2. So if you take this here and make it, this will actually become 4 by 3 delta by L. Similarly, the B part, if I do tau naught, it is again not difficult. Let's recall this is v1 square, this is v2 square delta by L. And we evaluated this to be 1 minus 8 by 15, right, into delta by L, or this becomes 7 by 15 into delta by L into rho u square. And if I were to do it with skin friction coefficient, it will become tau naught into rho u square by 2. And if you rearrange, this will become 14 by 15 into delta by L. And actually both these answers, specifically this answer, is very close to the actual solution. I want you to recall that we discussed this in the lecture. The delta by L scales as Reynolds number is power of minus half. Similarly, skin friction coefficient scales as Reynolds number is power of minus half, but there is a prefactor here close to 1. And this answer is very similar to what is actually there in the real full solution, something that we have not discussed, the exact solution, which is known as the Blacher solution. But you can look at these correlations in chapter 3 and you can see for yourself that actually this does a pretty good job. Macroscopic balance does a pretty good job. So let's go back again and revisit the whole problem slowly. And the whole point of this exercise was to actually make you see that we can actually connect the boundary layers to macroscopic balances, and there are some insights to be gained. So we started by saying that what we have here is some flow going through over a flat plate, which leads to this development of boundary layer. We said we will analyze two cases: velocity profile which is linear, velocity profile which is quadratic, both of which have velocity 0 at the bottom here, and then velocity of free stream velocity at the top, right? And we want to find the value of the shear stress, average shear stress on this entire plate because of fluid flow. So we said that this has some similarities in what we have discussed in macroscopic balances, where we were trying to find forces due to bends because of flow, forces on some solid surface because of flow. So now we are also trying to find the force on a flat plate because of flow. For macroscopic balances, we need a control volume, we need the information of pressure, and we need the information of velocity. The information of velocity has been given to us in the form of the velocity will be constant everywhere here. It has been given to us, and we know the velocity profile within the system as part A and part B. Right? Information of pressure was straightforward, that it is equal to u du by dx, where u is the capital U, and the free stream velocity does not change over a flat surface. That is something we have discussed, and that is physically also true, that the velocity won't change based on the position. But if there was a curved surface, it would change. But this is a flat plate, so it doesn't change, and pressure remains constant. We choose a control volume, which was of the height delta by delta of L, and we did that because if we choose a bigger anything higher than that here, you can imagine that that contribution would get cancelled with the contribution from the here, because the velocities are no longer exactly the same on both the sides. So it would no longer matter to have the control volume above that. So we took the control volume as this, and then we realized that there are three surfaces out of which this surface does not have a mass in flux, because velocity is parallel to the surface. Because there is no mass in flux, it cannot create any momentum in flux either, right? So we wrote down the expression for f star based on the normals, pressure, and velocity square average. There is a surface area which I initially forgot, so please to correct that. Once you do that, the pressure cancels out because pressure does not change, and then it's a very simple expression of v1 square minus v2 square averaged. Using f star as tau naught into length into w, which is the length because stress acts on this side of the plate, this part of the plate. We can just get the tau naught in terms of delta by L, and all we need to do is evaluate. So v1 square is simply u square because velocity is constant everywhere here. So mean is also mean square, everything is basically just u. So mean of the squares is equal to u square. But here we have to evaluate based on the velocity profile, two of the velocity profiles given to us. In one of the cases, first case it comes as u square by 3. In the second case it comes as 8 by 15 u square. There's a little bit of math here, but I think it should be pretty easy to follow what we did. Just square it and do integration. Okay. And again, if there was no difference in the velocity was assumed to be constant here, that it will be capital U, this v2 will be u square also, and it will become u square minus u square and it will become 0. Which is an important insight that for boundary layer is the reason for the drag. If there was no boundary layer, the velocity will be u everywhere, and that will no longer have any drag, which was the Lambert's paradox. So it is important to recognize that there is a velocity profile, and that which creates this v2 square mean concept, and that's why you get this difference. Anyway, once you do that, you can express tau naught in the function of rho u square times some delta by L. And then we recall that there is a skin friction coefficient definition we discussed in chapter 3, just to make it dimensionless. We do that, and we find that Cf is 4 by 3 delta by L, or C for part A with the linear velocity profile, and Cf is 14 by 15 delta by L, which is the parabolic velocity profile. Specifically, this part is very close to the experiments. Just a quick note that delta by L goes as Reynolds number or minus half, so Cf is also going to go as Reynolds number is minus half, and that's true. So please go on to chapter 3, and if you want to just see the correlations that we discussed once also back in part first, actually follow. So I hope this was just an interesting example. We just thought it would be useful for you to go through a boundary layer and do a macroscopic balance on a boundary layer, and actually see why there is a drag, and if there is a drag, it is because of the mean square of the mean of the velocity, and then we have to consider velocity profile to calculate the drag. And hopefully this exercise is interesting and useful. And if you have any feedback, please feel free to give us. Thank you.